a triangle when I'm trying to rack pool balls. Hey, maybe you're on the other end and there's balls on that end and balls on this end, and you're getting ready to rack the balls and somebody's tossing them in the rack. And then you quickly move that rack up to the dot and you hurry up and pull the top of it off, right? If you hurry up and pull the top of it off, what will happen? Your balls are going to start running. Okay? And so we got to have something to corral this. And notice when he corrals the actin, how he corrals. He likes to keep his holes blocked. So the tropomyosin is over the top of the active sites of the actin molecules. All right? Third protein. I like to call this my Mickey ears. This, and this. They're called troponin. And so located at regular intervals on the surface of the tropomyosin, made up of 3 types of troponin. Well, let's start with the most logical first. One of them is attached to the tropomyosin. His name is troponin T. One of them is going to bind to calcium. His name is troponin C. One of them is going to bond to actin. Uh-oh, we were on a roll. T, C, and why don't you name it A? It's not. It's troponin I. So one's attached to the actin, one to the tropomyosin, and this guy ready to get the calcium. Without calcium, you won't ever uncover these holes. If you don't get your holes uncovered, then your myosin can't stick in there. Okay, so it's extremely important that we're able to cover them at rest, but then open them whenever we want to work. And so the thin filament, 2 helical rows of actin balls with an active site that has what in it? ADP. ADP. Okay, then we have tropomyosin that does what? Covers my active sites at rest. And then I've got 3 kinds of troponin. The one that attaches to tropomyosin is troponin T. The one that attaches to calcium, C. And the one to actin, I. Troponin I. Now, why do you care about that? Any of you working clinically besides Tanya? Letitia? I know you're aware of it. We draw troponins all the time. Okay? Every time somebody's threatening a heart attack. Every time somebody is threatening muscle injury, we're running troponins because it's one of the first proteins to increase in muscle stress. And I assume, Letitia, you know, our hospital, as soon as you came in with chest pains, you bought yourself troponins 4 times for the day. Yep. Yeah. Is that pretty standard for you too?
Serious, yeah.
Yeah. And so our first one, of course, we do one in the emergency room, and then you do one like 6 hours after that, and then 8 hours after that, and then 10 hours after that. And if they stay low, we can pretty well say, no, you haven't had a heart attack. You're not going to ever see that heart muscle, but you're going to see those blood tests. And that troponin is so important for us to be able to see that that is taking place. All right. Third protein. Dystrophin. A rod-shaped muscle protein that is found inside the muscle cell membrane. What's a muscle cell membrane called? Sarcolemma. He's inside of here. And what does he do? He protects a muscle cell from overexerting itself. So I might wake up, which I didn't this morning by any means, and say, I'm just going to go to the gym and bench press 300 pounds today.
Impressive.
Impressive, yeah. Even in my good days would I never have been able to do that. But even if I had that crazy thought, my muscles would say, no, you're not. Because if I blow you today, you're gone. You don't get any more of me. you have made a decision that's not appropriate. So inside of my sarcolemma is this protein called dystrophin that affects me against powerful forces. And so it's supporting them against the powerful force of a contraction. Without this, you'll do something stupid. Your muscle cells will die, and then you have less to do what you thought, and now your dreams of doing 300 pounds will never be there. Do I have problems with this protein? Absolutely. Children can be born missing this minute little bit of protein and have the disease called muscular dystrophy. So today they may try to get up, and when they did, they blew a muscle cell. And so tomorrow they can't get up. Okay? And so how many of you know somebody, at least personally, with that? Okay? You know, it's a very degenerative disease. Now, there's several types of muscular dystrophy. If you ever take my pathology class, we'll get into a little bit more detail. But the type we're talking about today is called Duchenne's muscular dystrophy. If you ever watched Jerry Lewis's telethon on Labor Day weekend, I guess this is still called Jerry Lewis.
I don't think they do it anymore.
Do they not do it? Okay, well, you know, for years that was the standard, you know, what was happening on Labor Day. And the poster child for that almost always was a boy. Why? Because Duchenne's muscular dystrophy is what we call sex-linked. So that means you got it from either your dad or your mom. But it's what we call recessive. And so boys only have to have one copy of it to get the disease because it's carried on the X chromosome. Boys have what chromosomes? X and a Y. For girls to have it, they have to get a copy from both their mom and their dad. Now we'll get into genetics in A&P too, but I'm just going to show you the difference here for a minute. Okay, this is an X chromosome, and we use a capital letter to denote that that is the dominant trait. So I'm going to say D says it's the trait for dystrophy, and dominant says I shouldn't have it. Most people don't have it. But your mom could be carrying the recessive trait that if this shows up, okay, in a boy, one copy, they have it. Mom looks normal because this masks that. But when she passes this one down to son, he has this. And one copy of a recessive trait on mama's gene says mom didn't have it, but son will. Now for a girl to have it, she would have to end up like this. A little copy from both mom and dad. Well, the only X dad's got is this one. And if dad's got this, that means he already has it. And he ain't having sex. By that time, he's probably not going to be able to father children. So you're not going to see that hardly ever in women because of what the disease does to the men. But mom looks totally good, son now carries that blind copy she didn't know she had. Now that's one type. There's other types of muscular dystrophy that are carried on the dominant trait, Beckett's muscular dystrophy. So every time you see a muscular dystrophy, you just can't walk up and say, okay, hey, you got this from your mom, didn't you? Okay, you just can't make those assumptions. But I know there was a family, and I don't know their names for sure, but from Washington, Indiana, the people that own the Amish restaurant up there. What was
Black
that?
Buggy?
Black Buggy. Okay. There were several sons in there, and you know they've tried to do restaurants in different places. And right down the road here, there was a place called Mike's. Okay, for a short period of time. If you ever were in there, one of the boys was in a wheelchair running the cash register. I don't know if you ever noticed that or not. But somebody told me there's like 5 sons in that family.
They all have it?
They all have it.
Oh my.
But you know what happens Okay, now, I don't know, like I said, I don't know the history, so please don't quote me, that I'm saying this is the gospel truth. But I don't know whether they're Mennonite, if they're pure Amish or what have you. But I could probably only guess that the kids are probably very close in age. Which means that by the time they were becoming symptomatic, the others were already born. Okay? And you can't stop something that's already in the works. But imagine being that mother, and I don't even know. I don't know their history at all. So if I knew that I had passed a sex-linked disease on to my son, I would feel horrible. Because usually as a mom, what will we do? Please let me die before my kids are going to die. That's, exactly what we would be saying. And so, like, what's the worst case scenario? Zach or Gage, Corbin, any of you colorblind? Okay. If you're colorblind, you got that from your mama. A big deal. You're living in the right time because nobody cares what they put together anymore. Your socks don't have to match, your collars don't have to match. I had to know the color palette when I was a child because God forbid if you put two things together that shouldn't go. I don't even know what the color palette looks like anymore because I'm so confused on what's allowed to go together. So who cares about that? Hemophilia. Well, you're not going to die, but I certainly don't want you to have that either because that means you're going to have to take factor 8, and that has some risk with it too. So there's baldness. If you want to know if you're going to get bald, go look at your mom, right? That's her gene and her son's. You got the X from your mama. So there's a lot of genes out there that aren't death-defying genes. But when you carry something like this, you're like, oh my gosh. Knowing as a mom, you were responsible for carrying that. And you may go generations and never pass it on. Because when mom divides, there's a chance that they'll get this one, or a chance they'll get this one. And this is not, well, we had one here, we better not have another one because the next one will get this. No, this is every pregnancy. So obviously it's a crapshoot. You don't know, what you're getting in the lottery, particularly whenever you're, crossing over like that. And so dystrophin, a very important protein. Most people are aware of actin and myosin if they know anything about healthcare, but very few of them know about the one that's found right here, inside of my sarcolemma, that's going to protect me from doing these powerful things that I think I can do, but yet my muscle knows better than me. All right, so let's start putting it all together. Physiology of a muscle contraction. When a muscle fiber is at rest, the tropomyosin, troponin complexes, tropomyosin blocks the active sites, the holes on the troponin. When those holes are open, there's a little crossbridge thinks he needs to, put his golf club in there. Okay, and so we got to close those sites. Okay, and so if a high concentration of calcium is present, calcium comes in the picture. These three are all attached together, and the calcium, troponin C, he goes to reach for the calcium. Well, guess what? It's like sleeping in the family bed. When one rolls over, everybody feels it, okay? And so when calcium comes in the picture and he reaches out for the calcium, he pulls the cover off of the active sites. No calcium, muscles are closed. Calcium in the picture, open up, I can stick my heads in. Okay? And so if calcium is present, then the cross bridge is formed between the actin and myosin filaments. So where does calcium bond? To the troponin C. This causes a change in the position of the tropomyosin. This exposes the active sites on the actin filament, and now you contract, and what happens? Ratchet theory says these guys are going to come to the center. So now, for a muscle to contract, I have to have what first? A stimulus. I better be able to make sure that there's what here? Acetylcholine. I better make sure there's what on the other side? A receptor, hey? Start a new impulse, and that will trigger the release of calcium that is stored in these cisternae to go down the T tubule to hook to who? Troponin C. What does that do? Pull the tropomyosin off of the active sites. Okay? The myosin cross bridge will get into that, and what's going to happen? Sarcomere will shorten. Got it? No, I'm not. That was, are you serious?
Yeah.
No, that was a look like, what are you smoking again this morning type thing. Again, if you look at the physiology, it's driven so much by the anatomy. And so your contraction ends when? What caused the tropomyosin to come off?
Calcium.
So the contraction ends when calcium returns home. How does he go home? He uses an active transport system to take him back to that SR. What's an active transport system? It's going to cost you ATP. Remember, active says I use energy, and active transport systems are most of the time referred to as pumps, because pumps are taking energy to work. So the calcium pump sends the calcium back to the SR where he needs to live. Now, what also caused the problem? What came across? Acetylcholine. So you got to keep acetylcholine from getting over there. So how are you going to do that? It requires an enzyme to break it down. The enzyme is called acetylcholine esterase. And so it will break down the acetylcholine, so now you don't have any more contractions going on. When will you release more acetylcholine? When you get another stimulus. So as long as you don't keep re-stimulating, you'll get to rest. All right, we ready top to bottom? We receive what first?
Stimulus.
And it travels down my motor neuron to trigger the release of, and it does what?
Jumps across this.
The synapse bonds to receptors on the motor end plate, generates a new impulse going both directions through this,
Sarcomere.
and now stored in the cisternae are, that's going to go through the T tubules, and he's going to hook up with who? Troponin C. And troponin C will pull the tropomyosin off of the active sites, and a cross bridge can hook into it. And so how does it work? Cross bridge, link, sliding filament theory. We've contracted. Now how do we relax? Two things is going to make it go back to normal.
Return it to the calcium.
Calcium goes home, SR. How?
Calcium pump.
Calcium pump. And acetylcholine gets broken down how?
Enzyme.
Called acetylcholinesterase. And now the muscle rests. You got it? We'll see. All right, let's take a break.
Clear as mud.
No.
It makes complete sense, it's just getting it stuck in.